In this section, we're going to consider problems that use Newton's third law. Newton's third law states that any two bodies in contact exert an equal but opposite force on each other. We've seen this already in the idea of the normal reaction. If an object is sitting on a surface, the object is exerting its weight force on that surface, and the surface exerts a normal reaction of the same magnitude onto the object. We're going to apply it to this problem. A child of mass 12 kilograms is sitting in a toy car of mass 7 kilograms. An adult is pushing this car parallel to the rough floor with a force of 35 newtons, and there is a total resistive force acting on the car and the child of 18 newtons. We're going to take acceleration due to gravity as 9.8. First, we draw a force diagram showing all of the forces acting on the child. If this is the car, and the child is sitting in the car, the child's weight force exerts a force of 12g on the car. Because the car is acting as a surface, the car is exerting an equal force of 12g onto the child as a normal reaction. 12g is 117.6 newtons. We're going to treat the car and the child as one single body, therefore we're going to add the masses together. So 12 plus 7 is 19 kilograms. By treating them as a single object, we don't need to consider any internal forces such as the normal reaction, because it is now just one single object. The mass of the car and the child combined is 19g. The normal reaction is now between the car and the path or the road that the car is sitting on. A force of 35 newtons is acting on the car as an adult pushes the car. And because the surface is rough, there is a frictional force acting in the opposite direction to the direction of motion. So that is 18 newtons acting in the opposite direction to the 35 newtons. We know the car is accelerating horizontally. We know that vertically the car is in equilibrium. In other words, this weight force and this normal reaction are equal. So we only need to consider the resultant force in the horizontal direction. The resultant force in the horizontal direction, taking left to right as positive, is 35 minus 18, so 17 newtons. We can use force equals mass times acceleration to give us the acceleration of the car and the child. Substituting this in gives us an acceleration of 0.895 meters per second squared. The car and the child are a connected object, so this means they both have this same acceleration. We're now going to consider a situation where a stationary car with a mass of 1,000 kilograms is towing a caravan with a mass of 900 kilograms. The car is applying a driving force P from the engine, and the total resistive force acting on the car and the caravan together is 11,000 newtons. We're going to draw a force diagram showing the car and the caravan, given that they are connected by a rigid rod. So the car has a weight force of 1000 g and a normal reaction, which in this case will be equal to the weight force as the car is not accelerating in the vertical direction. There is a propulsive force or driving force from the car's engine of P. There is also a resistive force acting on the car. This is due to friction. There is then a connecting rod connecting the car to the caravan. The caravan has a weight force of 900 g and its own normal reaction force. And there is another frictional force acting on the caravan. There is also tension acting in the rod. Tension is acting on both of the objects as the car is pulling the caravan forward, and the caravan is pulling the car backwards. These two T values are equal and in opposite directions. We want to find the driving force of the car. Now, if we consider this as two separate objects, there are quite a lot of unknowns. We don't know T, we don't know F1, and we don't know F2. It would be easier if we consider the system as one single object, the car and the caravan combined. By combining them together, we can see that we no longer need to consider the tension in the rigid rod because it is now an internal force. We can also add the two frictional forces together, and we know the total resistive force here, so we can use the 11,000 newtons as F1 plus F2. This has simplified the model down. We can give this a combined weight force of 1,900 G and a combined normal reaction. If we put 11,000 newtons in as the total resistive force, we can see the car is about to move. It's not quite moving at the moment, it's stationary, so it's currently in equilibrium. At this moment, we can say that P must equal 11,000 newtons because at this exact moment the forces are balanced. We're now going to consider the system as two separate objects now that we've calculated P. We've also been told the tension in the tow bar. So we are told the tension is 5,300 newtons and we want to find the resistive force acting on the car. We only need to consider this part of the diagram now, as we are only concerned with the car. We can ignore the caravan for now. So the car has these 5 forces acting on it. So, acting horizontally, we can see that P is the forwards force acting on the car, and F1 and T are backwards forces acting on the car. As the car is in equilibrium, it's on the point of moving, but it's currently stationary. P must equal F1 plus T. Substituting in the values for P and T gives us F1 is 5,700 newtons. Now complete exercise 4.2 on page 228.